In this section, we're going to be able to sketch a curve without the use of a graphing utility. We're going to take information obtained from asymptotes, from intercepts, derivatives that will give us relative mins and relative maximums, and concavity in order to be able to sketch the graph. So we're going to start out by being given some graphs, and we're going to determine the asymptotes from a graph. Then they're going to give us a function that we're going to have to use some algebra and calculus to determine the asymptotes. And then kind of a tricky part of the assignment is where they're going to give us all this information and we have to sketch the graph. And then the last thing is we have to obtain all that information and sketch a graph. So let's start out with the easy part. As we look at a graph, we're supposed to determine the asymptotes. Asymptotes are usually represented on a graph by a dotted line. Well, you can see that on number 3, I don't see any dotted lines. Well, let's talk about horizontal asymptotes. This is where the graph is going to be flat out on the ends. So we ask ourselves, as x approaches positive infinity, as it keeps going out, what line, what horizontal line is it getting close to? Well, I think you can see that it's pretty flat at y equals to 0. That's the x-axis. And on this end, as x approaches negative infinity, we have a limit of 0 also. So we would say the horizontal asymptote is y equals to 0. But what about a vertical asymptote? Well, that's usually when the graph kind of goes way up high and gets closer and closer to something, or goes way down low and gets closer into something. And we usually see it as a dashed line. And I look at this and I say, okay, I think my vertical asymptote here is x is equal to 0. And these are the two axes, and they're pretty popular asymptotes. But let's look at number 5. Now again, the horizontal asymptote talks about the end behavior. As x goes way out here, how is this graph? Is it flattening out? Or way out here on the negative side, is it flattening out? And it certainly is that same y equals to 0. Now that's the end behavior, what's happening out in infinity and negative infinity land. The vertical asymptotes, it looks like they've drawn them in for us. Truthfully, these should be dotted or dashed lines. These are not actually part of the graph, just the blue curved part. Those would be vertical asymptotes because you can see the graph is going way up high and way down low. And so this vertical line is x is equal to negative 1, and this vertical line is x is equal to 1. So those would be my vertical asymptotes. This would be my horizontal asymptote. Number 7, it looks like they've also drawn in possibly the horizontal asymptote here. As x gets way out here, way to the side, how is it flattening out? What line is it approaching? What horizontal line? And that would be y is equal to 3. That's your horizontal asymptote. And then you can see how the graph goes down and down. It's getting closer and closer to the y-axis without ever touching it, and that would be our vertical asymptote. So how do we find those if we don't have a graph? The good news is that it's pretty easy. Okay, we've done it before actually. A vertical asymptote really just comes from the denominator. That's when the denominator cannot equal to 0. The horizontal asymptote, we're going to take the limit as x approaches positive infinity and x approaches negative infinity. Just to remind you, you had some questions like that on the first test. So let's go back and see how can we find the vertical and horizontal asymptotes of these given problems. But before I start, look right here. It says the graph of a polynomial function has no vertical or horizontal asymptotes. So problem number 17 and 18, those are not rational functions, meaning they're not a fraction. And so right here, automatically, we know that there are no asymptotes. But let's go to where there might be. Let's look at number 11. The vertical asymptote, you look at the denominator, and you set that equal to 0, and that is your horizontal asymptote. All right? Go back to domain, that says the function cannot be defined at 0 because we would be dividing by 0. So we represent that in the graph by a vertical asymptote. Hopefully you remembered that from college algebra as well. Now, the horizontal asymptote, we're going to take the limit as x approaches positive infinity of 1 over x. I don't know if you remember how to do that, so we're going to go over it. You're going to divide each term by the highest degree of x found in the denominator. So we're going to take the limit as x approaches infinity of 1 over x, x over x. And remember, this is 1. And so as x approaches positive infinity, as x gets really, really large, this value is going to approach 0. So we have a horizontal asymptote at y equals to 0. Don't forget that y, it is a horizontal line. If I went back and put a negative infinity, you would still get 0. All right, let's look at number 15. The vertical asymptote comes from the denominator. Set that equal to 0 and solve for x, and that's your vertical asymptote. That's where x, the value of x is undefined or makes that function undefined. The horizontal asymptote, we're going to take the limit as x approaches positive infinity. Right, so the biggest power of x is x. So if I divide everything by x and then take that limit, okay, remember 1 over x, that approaches 0, that approaches 0. That's 1 over 1, so we have a limit of 1. So my horizontal asymptote is y is equal to 1. And again, if I went back and did it for negative infinity, I would still get positive 1. So there's my vertical asymptote and my horizontal asymptote. Certainly probably get a little bit more difficult. So let's look. Okay, so my vertical asymptote, set the denominator equal to 0. In this case, solve for t. Don't forget your plus or minus sign. So we have two vertical asymptotes when t is positive 3 and t is negative 3. Our horizontal asymptote, we're going to divide every term by the highest degree of your variable in the denominator and take that limit. So the limit as t approaches positive infinity. Right? And again, when we have a number over a variable approaching a very large number, that limit is 0. That's 1 over 1, which is 1. So my horizontal asymptote is y is equal to 1. Right? Same process here. Vertical asymptote, set the denominator equal to 0. This time I'm going to have to factor. So those are my two vertical asymptotes. Then for the horizontal one, I want to divide every term by the highest degree of x in the denominator. So that would be x squared. Then you could go through and reduce. Hopefully remember from chapter 2 that this is going to cancel out an x, and so that has a limit of 0. That's 1. That's 0. That's 0. So what we have is 0 over 1, which is 0. So my horizontal asymptote is y is equal to 0. So number 23 is in an odd format, but we still have a rational function because we have a denominator, and it won't be defined if the denominator equals to 0. So for the vertical asymptote, I'm going to set my denominator equal to 0. Yes, it was squared, but I would take the square root and it would go away, and then solve for x. So I have one vertical asymptote at x is equal to 2. Now, how do I do that horizontal asymptote? Where I'm going to take the limit as t approaches infinity of 2 plus 5 over x minus 2 squared. And I think I used x's and that had t, so I'm just going to go back and make all those x's. This doesn't have an x. This has an x in the denominator. So we should say that when you have a number over a large number being squared, that limit is going to be 0. So you're just left with that 2. So my horizontal asymptote is y is equal to 2 as well. That one's a little bit odd, but not real difficult. So now we know how to find the vertical and horizontal asymptotes. Well, what about graphing it? What if they give us all this information? Okay, yes, I know you could reach for a graphing calculator and plot that. However, you won't be allowed to do that on the test. So let's see what we would have to know. They tell us the domain is all real numbers. A y-intercept. We know there's no asymptotes because it's a polynomial. But then, what is all of this? Intervals where f is, that means increasing, that's decreasing. So it's telling me increasing from negative infinity to 0, and then 2 to infinity, and decreasing from 0 to 2. I've got relative extrema, I've got concavity, and I've got a point of inflection. What all can I put on the graph? Well, I'm just going to sketch it. The y-intercept is 1. I think I can handle that. I have a relative max at 0, 1. So I know that's a maximum, and a relative minimum at 2, negative 3. It's concave downward from negative infinity to 1, and then concaved upward from there. Ah, my point of inflection, that might help. 1 to negative 1. So I've got that. Let's see. So it's concave downward, and then it's concaved upward. What else have I got? It's increasing from negative infinity to 0, and then 2 to infinity. So here's 2. So I could say, well, it's increasing. That sounds good. And from negative infinity to 0, well, if this is a maximum, I had to get there. So I'm just going to say it got up there. It says it's decreasing from 0 to 2. And yep, from 0 to 2, I went downhill. I think that's a pretty good graph. Go back and look at this graph on a graphing utility and see how close we got. Now we've got some other interesting things. So I'm just going to plot any points I have and any asymptotes. So I'm looking for points. All right, well, oh, an x-intercept at positive 1. X-intercept at positive 1. I've got asymptotes on the x-axis and the y-axis. Now remember, the horizontal asymptote, this one, means it flattens out. This one means it can't touch it. We have a maximum at 2, 1. Do I have anything else? Ah, a point of inflection. Out 3 and not quite up to 1, 3 and 8/9. All right, remember, a point of inflection is where it changes concavity. All right, so it's concave down from there to there, and it's up from 3 to infinity. So let's see, that's 2 and that's 3, and this is a point of inflection. That means it's got to go down, and then somehow it's going up. But I know I can't like curve up because I've got this asymptote that says flatten up, but that's still curved upward. Okay, so downward from 0 to 3. Let's see, if it's concave downward, and I've got this, I don't know, maybe I need to read the rest of it. What about these intervals of increasing and decreasing? It says it's increasing from 0 to 2. All right, so decreasing from 2 to infinity. Ah, that's why I can't have that. It can't go up. It has to continually go down, down, down. All right, but I want to go up from 0 to 2. And I've got to cross the x-axis. So I think maybe something like that. So it's concave downward, and yet I'm increasing from 0 to 2. What's going to be on the other side? What's happening? It's decreasing from negative infinity way out here to 0. So how could I be decreasing, not cross the x-intercept, not cross the x-axis, because I only have one x-intercept? I think maybe something like that. Right? I've got to obey the asymptotes. The x-intercept says it only crosses the x-axis one time. It cannot cross the y-axis because that was a vertical asymptote. I know that seems hard, and it is. We're going to practice. I think it will get easier once we do it on our own. So how are we going to go about sketching our own graphs? Well, the book gives an outline, as I have here. You don't have to memorize that. I will certainly prompt you on the test, like what is the domain, what are the intercepts, and things like that. Right, now here, determine the behavior of f for large absolute values. That's the same thing as the horizontal asymptote. Not too sure why that's in there twice. So we're just going to stick with the asymptotes here. We've got it be intervals of increasing and decreasing, so that's the first derivative, and find that relative extrema. And then we're going to determine the concavity and inflection points, and then we're going to plot a few more points. Remember, you're not going to be using a graphing calculator, but you may use a regular calculator. All right, so let's start with this problem. Okay, so the y-intercept is found by evaluating, letting x equal to 0. So hopefully you can see that's 0, 0, 0, and we would have 2. So that's the first point we have to graph. Right? The x-intercepts, you let y equal to 0, and you would try to factor or somehow solve for x. So I see this as that I would have to maybe group. I'm going to try that. Well, those don't match, so that doesn't work. I could try regrouping, but it just does not factor. And so if you read the book, it says if you can't find the x-intercepts easily, then blow them off. So I'm going to say this is not easily found. You don't have to worry about that happening on the test. I'll let you know if I want you to find the x-intercepts, which means you would be able to do them. All right, the next thing we need to look at is intervals of increasing and decreasing and extrema. So let's go through that first derivative. I skipped the asymptotes because this is a polynomial function, so there are no asymptotes. This is a nice smooth curve, imagine like a roller coaster. Right, so in order to find intervals of increasing and decreasing, we take the first derivative, we set it equal to 0 and solve for x. We put those on the number line, and we pick points in each region and evaluate the first derivative to see where it's increasing or decreasing. All right, so this is negative, so that means it's going down. This is positive, so it's going up, and then it's going down. That tells us about our intervals of increasing and decreasing, so we need to write that down. I also know that I have a relative minimum there and a maximum there, and I need to evaluate those numbers as well. Remember, I need to come back up here to the function to get any y values on the actual graph. So in order to find my relative extrema, I know I have a minimum when x is -1. So I need to evaluate the function at -1, and that's -5. Remember, that's a minimum. And then I have a relative maximum at x is 2, and I have the point 2, 22, which is again a maximum. All right, so I have increasing and decreasing and a min and a max. I believe the next thing I have to do is figure out the concavity. So I'm going to come back up here to the first derivative and take the second derivative, set that equal to 0, put that on a number line, test regions. So I know this is up, this is down. I also know that since it changed concavity, I have an inflection point when x is 1/2. Of course, I have to figure out the y value. So again, I have to go back up to the function and let x equal to 1/2. And again, don't use decimals. Your calculator should be able to handle fractions. All right, so I have an inflection point when x is 1/2, y is 8.5. All right, so I'm going to put all of this together. Okay, so we had a y-intercept. All right, so here is what we found with all of our work. I like to list all the points on the graph here. So those are actually points we're going to plot. This is going to help us connect those dots in the correct manner. Okay, keep in mind this is a polynomial function, so there's no asymptotes. All right, so let's take this information that we've obtained. We have a y-intercept at 0, 2. We have a relative minimum at -1, -5, so that's a min. And then we have a relative maximum way up here at 22. We have an inflection point about midway between. All right, let's see, what about that increasing and decreasing? It's increasing from -1 to -2. So from -1 to +2, it's going up. So from here to here, it's going up, we can tell that. But what about the concavity? Well, it's concaved up from -infinity to 1/2. So right about here, I'm going to move that over a little bit. That's not quite at 1/2, so I'm going to move it up here. So somewhere about right here. The concavity changes, and it's concave downward from 1/2 to infinity. I think I'm going to take that right here. So from 1/2 It's concave down, it's reached a max, which means it's got to come on down. Then it's concave upward, it's got to go through here, it's got to reach a minimum, perhaps something like that. It would have been a lot more helpful if we could have indeed found those x-intercepts.